These are the kind of stimuli that the person sees while they're lying in the scanner, if you can imagine that. And they're asked to make judgments. Are these the same face or not? And are these the same chairs or not? And we measure the degree of activation while you're making the judgment about faces as compared to the degree of activation while you're making judgments about non-face stimuli. And here's what we find for people with autism. Let's start with the normal individual. When the normal individual is making those judgments about faces, this more medial part of the temporal lobe becomes active, whereas making judgments about objects, you can see another part of the brain is used. In fact, it's clear that there are very different brain systems that have evolved for perceiving faces as compared to objects. The individual with autism, when they're perceiving faces, is much more likely then to use this object part of the brain. Now, does this mean that people with autism cannot recognize other people's faces? No, not necessarily. They may be using areas of the brain that are less efficient and less using different kinds of strategies. We think that they use more of a piecemeal approach, looking at individual eyebrows and mouth as opposed to this holistic approach. And in some cases, people with autism actually may have frank problems with face recognition. In fact, just anecdotally, we had a man who worked for us for over 10 years. And it just so happened that one day one of our staff members was on the bus, and here was this man sitting across from her. And out of context, he could not recognize who she was. And we came to realize, even after having worked with him for many years, that he had no ability to recognize us by our face. And in fact, he used our voice. He was really good at voice recognition, but he also had made a point of memorizing all of the jewelry that the women wore and all of the clothing that the men wore. And of course, we thought this was one of his obsessions and preoccupations, and come to find out this was a means for him to compensate for his difficulty in recognizing our faces. Now, fMRI is very good at telling us where things occur in the brain, but it's not very good at telling us how fast the neural speed is, the speed of processing. For that, we have to turn to another technology, and that is electrophysiology, where we're actually measuring the electrical signals from the scalp. This particular method, particularly event-related potentials, or ERP, is exquisitely sensitive to the temporal qualities of neural speed. Now, what we do in an ERP experiment is we show stimuli, the same stimulus and comparative stimuli, repeatedly. And every time that stimulus is shown, we time lock the electrical signal and record it at the period time locked to that stimulus. Then we average it over several trials. And what happens is that the background activity that's not specifically related to that stimulus cancels out, and we're left with the signal that's specific to the stimulus of interest. Now, the nice thing about this technology is that unlike fMRI, we can use it with very young children. Now, to get a child to go into a scanner means that you'd have to have them lie perfectly still for 30 to 40 minutes. And not only can not children with autism do this, but most normally developing children cannot do this either. So the nice thing about this technology, and we call this high-density ERP because of the density of the electrodes on the scalp, is that we can put this net, completely non-invasive, completely painless net of electrodes on a child in under 5 minutes. And it can even be used with young infants to look at brain activity. So it's very good if you're interested in early brain development. Now here we have a young child looking at a face on a monitor while we're measuring brain activity. And it turns out that normal 6-month-olds will show a differential brain response when they see a face that's familiar to them as compared to an unfamiliar face, and a familiar object as compared to an unfamiliar object. So we decided to do this kind of experiment with children with autism. We had mothers come in, we took a digital photo of the mother's face, and we compared that to a digital photo of a stranger's face. And we also had the mother bring in the child's favorite object, not one that was an object of preoccupation, but just one that was of interest to them, and compared it to another object that they had not seen before. And here's what we found. Okay, Okay, this is the ERP of young children, so you can see what they look like. And let's start with the object stimuli. You can see here there's a significant difference in the brain response to the familiar object, which is in blue, as compared to this new object. In fact, the brain's saying, hey, look at that new object, it's more interesting. Whereas there was no differential response in the response to mother's face as compared to stranger's face. Now again, does this mean that young children can't recognize their mothers? No. For one thing, remember that we are showing these stimuli for 500 milliseconds. That's a half a second. So what we're looking at is the brain's ability to very rapidly distinguish between a familiar and an unfamiliar face, something that by 6 months of age the brain is easily capable of doing. Also, it may be that children with autism use other cues. They may rely on touch or voice or smell. We really don't know exactly how the children with autism are processing faces of familiar people versus unfamiliar people. Now, by about age 5, if we measure the electrical signal from this part of the brain in the right temporal lobe, a characteristic signal emerges in response to face stimuli. And let me just show you what that looks like. And what I'm first going to do is to show you the electrical signal in response to a non-face stimuli. And these are actual data recorded from adults who are about to undergo surgery. And before you do brain surgery, we often map out the different parts of the brain to make sure that you don't create any damage to areas that are important. So these are actual recordings from the surface of the brain in adults in response to different stimuli. Now here's what the response looks like to this flower. And here's what the response looks like to a face. And you can see this very robust and well-defined peak at about 200 milliseconds. So at about a fifth of a second, the brain is responding by saying, I know that's a face. So we use this to study neural speed processing in adolescents and adults with autism as compared to normal adolescents and adults, measuring EEG from the scalp. And here's what we found. Here are our data from our own my own lab where we're measuring the ERP from typical adults in response to stimuli such as these. And you can see that nice, robust ERP component to faces. At about here, we got about 170 milliseconds out. People with autism not only show a less robust response, but you can see it's delayed. And in fact, it's delayed by about 20 to 40 milliseconds slower. Now, why is that important? Well, it turns out to process signals from the face depthly, you have to be able to process information extremely rapidly. And even a millisecond delay can greatly impair your ability to track social information. Furthermore, you have to integrate that information online with other kinds of information. So when you're carrying on a conversation with someone online, you're processing all of those facial signals and the auditory linguistic signal and integrating them over time. So any of those systems are sluggish or get out of whack, it creates a lot of havoc and makes it very difficult, we think, for the person with autism. Furthermore, we think this may have therapeutic implications. It turns out that in another disorder, children with language delay, that they also found that the primary impairment was the ability to process the linguistic signal rapidly. And when they used a computer to slow down the auditory linguistic signal, they found that these children with language impairment could not only process the signal, but they were able to make rapid gains in their language acquisition. So we're very interested in the possibility that we can use these findings to develop some therapeutic techniques to help people with autism in their impairment in face processing. Now, we can also look at these signals across the entire scalp to look at the pattern of activation. And again, here's what we find. In typical adolescents and adults, you see this well-replicated finding that in the right occipital temporal region, you see activity in response to faces at about 170 milliseconds. Whereas in the person with autism, we're seeing a failure for the right hemisphere to specialize for processing of faces And you also see that they're using dramatically more of their brain to try to process that signal. And what we know from many brain imaging experiments is that the more efficiently and the more capable you are of carrying out a particular task, actually the less